and the biggest welcome to Jordan. We're so happy to have you here. Jordan Kemp is our visitor, and he's a postdoc at Oxford Internet Institute and the Geographic Institute. He got his PhD from the University of Chicago, and today he's going to talk about spatial relativity.
Thank you. Yeah, so I come from the Institute of New Economic Thinking, where we are blending complexity and economics, which you would think is like a match made in heaven, but it turns out economists not so jazzed about it. So we work at INET mostly on like agent-based models and other kinds of out of equilibrium models of economic processes like supply dynamics, or sorry, supply chains. Like I'm working right now on a project on studying the labor market. But what I'm going to show you guys today is something completely different, unrelated to work at INET. This is some work that's continued from my work in the urban science lab at UChicago with Louis Beck. And so if you're familiar with his work, some of this is going to look familiar. Some of it will hopefully seem a little bit new. And so to start. Yep. Okay. So first, I'd like to start with just defining what we mean by urban science, since everybody has like a slightly different definition. So what we really try to do in our lab is address the following question. At a microscopic scale, we have a lot of really wonderful social dynamical theories, some qualitative, some quantitative. Things that come from like the social sciences, things related to like health, things related to education, studying income dynamics, and so on. And this type of work typically is trying to understand how people make decisions, how they process their environment, and so on. And then, at the macroscopic level, where a lot of economists work, macroeconomists, we think about quantities like GDP, inequality, employment, and so on. And through a lot of history, these two fields of research were really developed independently. And what we try to do is try to just find mappings between these systems, find ways to essentially aggregate up. And to do so, we draw a lot of concepts from population dynamics, from ecology and biology, as well as some insights from biophysics and ecology. Sorry, biophysics. And what we're really trying to do is just really study these and make sense of these emergent behaviors and come up with better theories and models and so on. So what I did during my PhD was really addressing some of the limitations in a lot of modern macro theory. Economists are, of course, trying to address these concerns of heterogeneity, of bounded rationality, of randomness, but a lot of economic intuition at this point really, doesn't take these, or they take these for granted, which is quite problematic. And so I worked in the past on really just developing general principles of growth that are built off of these principles. And so this resulted in a few papers that all really thought about growth, whether that be growth of individuals' incomes, growth of like a firm, and so on, in terms of some really basic principles about the environment that these agents are behaving in. And so one of the papers was on how by introducing this idea of the environment, we can really explain heterogeneity across agents in terms of decision-making relative to that environment, how that heterogeneity can then really introduce inequality, persistent inequality that's difficult to address through like standard redistribution methods, but that heterogeneity can also be beneficial, and that it allows for, or it enables like complementary behaviors that could promote cooperation. And so what I've been doing since my PhD is really to try to find ways to make sense of the environment. Essentially, how do we measure this general quantity that we rely on? And in doing so, I've been working to like identify patterns of growth, understand how that relates to and how that could predict inequality. And a lot of this work involves really doing distributional analyses and developing theories of distributional dynamics. And so as an example of what we're going to talk about today in an urban context is thinking about how distributions can change over time through these these popular sociological notions of like neighborhood selection. And then we're going to introduce some mechanisms to think about that across scales, really aggregate up. And so just to make this more concrete, the challenge is how do we identify these macro patterns in heterogeneous data? And how do we, in developing aggregate quantities of change, for example, like population growth, like income growth across a city, how do we calculate these aggregate changes without losing some of those microscopic patterns? I should say, by the way, I talk kind of fast, so if at any point you guys have questions, please feel free to just pull the stop for the question. And so this, of course, is not like a new problem. People have been working on this for decades. There's been a lot of really great work from both economists and sociologists, but what you find is, like I mentioned earlier, the economists tend to either ignore the heterogeneity or calculate in the heterogeneity in this very static picture. So we lose insight on how that heterogeneity evolves over time and how that could motivate future dynamics. And then there's a second component that we're really focusing on, which is the recursive nature of really just social identities. And I'll talk about this in the next slide. And so people have recognized the importance of developing theories of social dynamics that are recursive, but these have been largely like qualitative in nature. And people have really struggled to figure out like really clean ways to develop recursive aggregating descriptions of social dynamics. And so in this talk today, we're going to really define some nice, two nice formalisms for aggregating both incomes across a place as well as the changes in those incomes. And we're going to do so by applying some concepts from theoretical ecology and information theory. And so the two questions that we're going to be really asking here, the first is, what do these distributional differences across space and across scale reveal about neighborhood complexity? That's one, and that's going to rely on information theory. And then the second is then, how do we then preserve local measurements of change as we're aggregating to produce these summary statistics of social dynamics? Okay. So this is the outline. First, the second part of this talk is going to be addressing that first question, and then part 3 will get into that second question. So cool. Okay. So to start with this discussion, we're going to get really general and vague here, and I want you guys to think about what makes a New Yorker. And so usually when you're asked this question, I think people would go to one of two places. Either one, you think about what is a representative agent. So you think about a literal New Yorker, maybe he's defined by a certain kind of job, fashion, income level, et cetera. Or you would think, New Yorkers are so heterogeneous, you can't really answer this, but you could at least say there is a feature distribution that many New Yorkers might share. But then what if I asked you then, what if we got a little bit more granular? Now we're thinking about neighborhoods, right? So a Brooklynite and a Bronxite are going to be, that might conjure a different distribution in your mind, a different representative agent. I could get even more specific to somebody in the Lower East Side of Manhattan or Ridgewood in Queens. Maybe now we're talking about somebody who's more likely belongs to an immigrant community, who's more working class, and so on. The point is that the typical of a place encodes some distributional information. And as we get more specific, that information is going to become also more specific. And it's also going to encode some of the environmental conditions that those agents inhabit. And I just realized there's a screen there, which is really nice for everybody here. But keeping in mind that the more we aggregate, the more we necessarily are going to lose information. We're going to increase our generality. And that's of course, like a generally recognized problem of coarse graining. But what I'm going to show you here is that we can still hold on to more than you might expect by resisting the urge to like take means or take moments of distribution. So to start, here's a map of mostly Manhattan, where we've colored every census block group by the log of the mean income. And so you see here, like Manhattan is very green, mostly high income. Upper Manhattan is quite wealthy. This part of Brooklyn, this part of the Bronx is pretty low income. And then, we have these three neighborhoods here that we're going to reference throughout the talk. And so the first thing I want to mention is that this isn't just some like instantaneous snapshot of dynamic of incomes that could change completely next year. Like this is persistent across years, potentially even generations. And these are also representative of decades of choice. The complexity that's captured in this map is also represents the complexity of human behavior as well. So there's really quite a bit of richness by looking at this type of looking at the data this way. But then when we take a step back and just look at the aggregate distribution of the city, which is what we're doing in this plot here. So on the x-axis is mean incomes, on the it's a histogram. It's a normal distribution. So when we aggregate, we get some actually really clean, nice kind of behavior. So when you zoom out, it looks pretty simple. Now, when we zoom back in and then look at this income distribution, and this is using the binnings from the American Community Survey, you start to see, of course, that cleanness starts to dissipate. There's obviously more complexity here going on. And so we can think about this transformation from this aggregate distribution to these really local distributions using this reweighting matrix, WLJ. And throughout the talk, I'm going to have all the variables defined here, so you can please reference them. But what we're doing here is we're saying, okay, to introduce the context of this neighborhood, we're going to reweight all of these incomes using this reweighting matrix. And I just want to point out quickly that the structure really reflects the way that selection updates distributions of genes or phenotypes in a population. And so we're already starting to see, just by conditioning our distribution, we're starting to touch on a bit of the ecological literature. And so we would call this like a fitness update to a population. Here, there's no temporal. This is just, assuming it on a map, but it still has like a quite analogous math structure. And so if we ask now what this reweighting matrix looks like for our distribution of incomes, we start to see strong evidence of sorting. So this is the green represents these high income bins, high income weighting elements. And so we see, parts of lower Manhattan, midtown Manhattan, downtown Brooklyn, these are areas where high income people have essentially sorted into. And then we also have our low income matrix weights, and we see that those low income areas that we highlighted earlier have pretty strong weights there. And so now back to the nature of this weighting matrix. It also has a really nice analog to Bayes' rule, where now this weight matrix takes the form of a likelihood, which probably is a bit more of a reasonable comparison for us, since we're not doing ecology here. And what this weighting weighting is doing is really just telling us something about the local information, which is nice. But most importantly, by taking the log of this likelihood function, essentially, and then doing some averaging over our dimensions of our distribution, we can get this information quantity. So this here is a callback linear divergence. It's really measuring the difference in information space between these two distributions. So this distribution being like the citywide distribution, and this one being like our particular neighborhood or our particular income slice. And so what this then is measuring is essentially how different is my local distribution from the citywide. Where if this is 0, then the two distributions are essentially the same. We have a spatial unit that is representative of the whole city. And as maybe we get our distributions get more and more different, this quantity is going to increase. And so now we're going to plot this DKL for every neighborhood, and we can start to see, we see quite a bit of overlap, quite a bit of similarity here between this information map and this income map. But these are quite different. Yeah. Oh, okay. These are quite different in that what we've done here is we've really just taken a summary statistic of our distribution, whereas in this plot here we're doing a we're comparing our distributions at every point on the measure space. So we're really asking how different are these distributions versus here, this is, just a value. And so you start to see, like I mentioned earlier, the bigger the number is, the less similar this neighborhood is to the reference distribution. This is also telling us something about how complex is this environment in the city, the environment being this neighborhood, relative to this whole city. So for example, if we were to develop a theory of local change for this neighborhood, it would have to at least be this complex, is a way to read it. Yeah. And the nice thing we see is that the most representative neighborhoods, so here that would show up as gray, as dark gray, they tend to be usually more middle income. So in this range, so like we have some light green, light orange here, that corresponds to these gray parts here, as well as this little guy here, so on. So now we can perform the same calculation, but instead flip the order of the averaging. So just to go back, actually, see what we do here. So here you see we're averaging over L, but we could also average over N. And if we average over N, we now are asking a question about how well are our incomes sorted across neighborhoods. And so, yeah, so what we see here is something that is in quite a good agreement with a lot of the sociological literature on income sorting, and that high income and low income people tend to be quite sorted throughout the city, which you can guess are for some obvious reasons. One is by choice, one is from a lack of choice, whereas middle incomes tend to be the most the least sorted. So you find them. So yeah. Any questions so far before I move on? Cool. So then we can essentially, instead of averaging over either dimension, we average over the entire distribution to get like a single information value that tells us essentially how complex on average is your city. And we can do this for all American cities, or at least like a large enough sample size. And then ask, okay, on average, how complex are our cities? So we did this for 2010, 2015, and 2020. And you can see that there, between these 2 years, there wasn't much change, but from 2015 to 2020, there was quite a sizable increase. This is suggesting that over time, our cities are becoming quite a bit more sorted, quite a bit more complex. And then any subsequent model that would try to explain the data must be able to generate this level of complexity. Yeah.
Sorry. Here, complexity, is that the divergence of neighborhood? Is that what you call complexity?
Yeah, so by complexity, we mean to explain this data, if you were to develop a model of like neighborhood selection, of residential selection, your really simple null model could be just some kind of diffusion process, right? In that case, every neighborhood you look at would result in a Gaussian distribution, more or less. Now we start to add in effects like maybe there's some high income. You could add in some like homophily condition, or some attraction to points of interest, or to high income jobs, or you could add in. This is what I mean by complexity, like essentially. More terms to your model, essentially. And those terms, if they're well calibrated, would result in not only decision heuristics that are more complex, but then more spatially featured data. So a more sorted population along lines of whether it be income or identity and so on. Yeah. Yeah. Okay. So far I've shown you guys how information theory provides us a really nice temporal snapshot of neighborhoods. But can we measure how these dynamics compound over time? And that's going to be the next part of this talk. Okay. So we're going to shift gears a little bit And now we're going to talk about Chicago. And Chicago is a city that's for the last couple of decades has had pretty stagnant population growth. And so some people, you read in the media that Chicago is a dying city, that it's, we know obviously that a city could have, stationary aggregate dynamics, almost to be non-dynamical, but at lower levels of aggregation could be highly dynamic. So that's what this plot here is showing. So each rung on the y-axis is a level of aggregation within the city. So these are census block groups, census tracts. In Chicago, they have an extra layer called community areas, and then this is across counties. And so you see as we aggregate, and then this is like the 95% confidence of the distribution. And so you see as we aggregate, we lose a lot of that variation. We see a bit of shifting, which I'll explain throughout the talk where that comes from, what that tells us about how this place is changing. But this is just to show that even though at the aggregate level we have quite, there's almost no change, when we disaggregate, we see quite a strong amount of heterogeneity. And we can view this visually. So on the left side, we have the growth rate of population across tracts within the city. And where orange means the growth rate was higher. And this is between 2019 or 2014 and 2019. And so this is telling a pretty rich local story that people have been moving in mostly along the lake. So just to orient us, this is the lake, the downtown is right here. University of Chicago on the south side is roughly about here. So they've seen a lot of population gain along the lake, and then along some of these inland south side neighborhoods, a lot of population decline, inland west side neighborhood decline, and then north along the lake has been pretty some low growth. And then we can see quite a different story in the income growth rate here on the right side. So we see quite a bit of high growth along this near northwest side corridor, which if you ask people familiar with like local change in Chicago, they would say, there's been a lot of gentrification here, a lot of gentrification here. There's, you see negative growth in these inland south side neighborhoods. The point is that these dynamics are summarizing a lot of concurrent, very contextual narratives of change. And narratives that when we do really simple aggregation, like computing an average growth rate of incomes or population, we completely roll over. And so is there a way that we can essentially summarize this heterogeneity while capturing these local features? And so before we answer that, we can just also look at the distribution of our growth rate quantities. And as before, they're really nice, really well behaved. The growth rate quantities have they're fit to a T distribution. So that means they have quite wide tails. So there are some neighborhoods where over this time period, we see pretty consistent compounding effects, whereas maybe closer to the peak of the bell curve, maybe there's a bit more noisy change happening over the years. So to summarize this growth, I'm going to introduce two weighting functions. One is going to be a really simple population weight. So as we take an average across incomes or across the spatial units, we're just going to multiply by the population and then divide by the total. And then the second one, we're going to call a trait weight. We're going to pick a trait and then weigh that in our averaging. Here, we're going to pick income, so Y. And so this, I'm going to show you guys that this type of aggregation comes straight from ecology and tells us a lot about population compositions. This comes from the capital allocation literature. And so there's this really great paper that I'm going to be referencing throughout this talk here. And so to start with the first one, the first aggregation method, and this is going to get pretty mathy, so we can talk about this more later if you like, if you want to really go into the details. But this first population weight, we're essentially measuring the average at the later time minus the beginning time. And that Z is just going to be the log of incomes. And so this is really just a choice of, we have all these operators on our income. What is the order we pick them? In our case, we're first going to take the log, then the average, and then take the change. And Like I mentioned, we have this quantity Z. I'm going to also introduce this quantity W. That similar to what we talked about before, we call it fitness. It's really asking how is our population reweighting over time. So that's the same F as before. And so if W is greater than 1, that means this spatial unit has grown relatively to everybody else. And if it's less than 1, it's shrinking relative to everybody else. And so this is the price equation here. The price equation takes this aggregate growth quantity that we've computed this way, and it decomposes it into two really clean terms. This first term is just an average over all the growth of the lower units. So if, say, we were computing this for a tract, this is the average across growth rates of block groups multiplied by that fitness. So how much has this block group relatively grown or shrunken? And so this is really just like a straight up averaging where we've added in the fitness as a weight. And then the second term is where all of the really rich dynamics that we're going to study is stored in. It's this covariance term. And this is measuring really how is our population sorted here relative to the log income. And this is what we're going to use as our measure essentially of income sorting. And so are there any questions so far before I move on?
Yes, sorry, in this case, this K index, I got lost what this K index is referring to.
Yes.
Sorry,
So for a spatial unit J that has children K.
Okay.
So we're gonna,
okay.
we're gonna pick a tract.
So it's on the different like kind of orders of like space.
Yeah.
Okay.
And I'll have a visual demonstration.
Okay.
Slides to show this, but yeah, so usually J could be like some parent, K is some child, and then L is some grandchild of this hierarchy. And this math applies not just to spatial decompositions, but any kind of hierarchical system. Okay. And then now for this income weighting, the average looks just like this, where we, that 5 was from that previous slide. And now we're taking the expectation of the change in the log times Y. And when we do this, we're going to introduce this F, which is just relative income instead of relative population. And we see something really similar, where now we're averaging over the growth rates of the children. And then we get the selection term, where now we're selecting along the, we're really measuring how is our growth rate being allocated across our population. So if our low income block groups are growing more quickly than the high income, then this covariance would be negative, for example. And so those are the two aggregation methods. Like I mentioned earlier, we're just switching the order of these operators. And by doing that, we're capturing different population features, which is quite cool. And just the way to interpret it is really how are populations sorting along this quantity? Well, for us, this quantity is income, but you could pick anything that could be a sensible weight for your population. And then the second one is how is this trait redistributing? And so, for incomes, then it's income redistribution, but this could be, for example, like racial identity, occupation, so on. Do we have questions on how to interpret this? This is pretty straightforward. Okay. So, So now we get to the magic of the math, and that's following. So say we had like a price-like equation where we had some expectation value over the growth rates and some covariance between two quantities. Well, we could define a price equation for this guy in here as well. And so now this expectation value can be written in terms of the expectation value over an average. And then we can decompose that average into its own price equation. And then and then we can do this over and over and over again, and for as many levels of our hierarchy we have, which then, say we're studying growth across a system with many levels, like if we were doing national accounting, we could decompose our growth rate in terms of covariance across each levels of organization, across nations, if we were doing this for the EU, across regions, cities, neighborhoods, and so on. And then this is great because then we can start to measure and really think about like at what scale is this growth occurring? what factors affect growth at this scale? You know, for example, is this a scale where migration really matters, where the differences are from investments? Are these areas that we're analyzing rural or urban and so on? You can start to really think about at each level what could be a source of heterogeneity in your data. And so, and then just one last thing before we continue. You know, we have these nice shorthands. So this is trait times weight, trait times rates. And for the next part of the talk, we're just gonna focus on this first one, this population sorting. And then I'll show you a little bit of one half of a figure about the income sorting later, but this is still talk about. Okay. So now to demonstrate. So imagine we have a city that's bounded by this purple boundary, or a community area more likely. And then each of these block groups are then sectioned into two tracts, A and B. And that's given by the magenta outline. And so by looking at this data, we can do some calculation on, oh yeah, sorry. And then this money pile is the prevailing income. So if it's smaller, that means lower income. If it's orange, that means the incomes are increasing. If it's purple, the incomes are decreasing. And then this is just measuring how much the population is changing. And so I've, drawn this diagram so that there's a certain correlation there. We can calculate that, report them as selection effects. So for this unit, populations are growing, the relationship between population growth and prevailing incomes gives us a positive correlation. This one gives us a negative correlation. So we get two selection terms from that. Then we're going to aggregate our data using that method I showed you earlier. And then we can compute that selection effect again for the data here. And so here, I believe, there's essentially no correlation because actually here there is a slight positive correlation, I think, but it's almost negligibly zero. So we've aggregated our data now twice. We can compute an aggregate growth rate or a growth rate from this aggregate data. Report these selection effects. We essentially average these selection effects. And what you see up here then is like the price equation in action. And so for this community area, we've gotten a selection effect for the tracts, for the block groups, and then we've transmitted a growth rate from the data at the most disaggregated level. So does this diagram, any questions so far? Okay. But this lets us see pretty clearly now we can both simultaneously see selection effects at both levels of organization. And so now let's look at this in Chicago data. So on this left section here, we have selection across block groups within tracts. So that's being reported in this map. And then in this map, we're just averaging them to then show what those selection effects on average are for every community area. And so these community areas have populations of roughly 20,000 to 100,000 people. And then we can then separately compute the selection effects across tracts. Report, are you raising your hand? Sorry.
Oh, no, sorry.
Sorry. Then calculate at the tract level across tracts within communities. And so what we see here is that for this part of the city, this is like the near north side where there's historically a bit more wealth. This is a corridor that I highlighted earlier as having some recent investments, some recent demographic changes. But we see at the block group level, there's quite a consistently negative covariance, meaning that people are moving into low income block groups. Here, consistently positive, so people are moving into high income areas. We can do this for region 2, and in region 2 we see, and we would actually, before I move on, this is competing as in their opposite signs. So for region 2, this is closer to downtown. We see more consistent, across block groups, it's negative, and then across tracts, it's negative. Between these two, it's a little positive. And then in region 3, just generally, we see mixed effects. So here it's pretty mixed. Between these areas, it's also mixed. So this is all to say that the selection data that we observe between scales is quite heterogeneous. Spatially, it can also be heterogeneous, but there's also some nice consistency locally. And just to highlight earlier, like this should be consistent, at least spatially, as these boundaries are relatively they're obviously not arbitrary, but they do cross boundaries of mobility and often boundaries of infrastructure as well. So there's a lot of reasons to expect like spatial consistency. Okay. So now what I want to bring us to is when we then observe this data in the context of the raw growth data I showed you earlier, we can then start to build a more disaggregate hypothesis of what types of local change we're actually seeing in these neighborhoods. And so I've reshuffled the boundaries of our map a little bit, but now we're looking at this coastal part of the city, where this is the loop is right here, downtown area. Sorry, it's right here. Yeah. And so this is an area of high population growth, an area of quite heterogeneous income growth, but we see quite consistently negative selection. So since we know these neighborhoods are growing, that means that people are moving to consistently low income areas. And that would be consistent across like levels of aggregation. And so you could reasonably say, okay, there's probably some kind of investment, some kind of revitalization here, where we might look at other data sets and see a lot of construction, something that's allowing a pretty economically mixed group of people to move into this area. Now, when we look at our second region, now we see an area where there's, some slight positive, but pretty modest population growth, quite a bit of income growth. But all of this population, all of these population is moving into consistently high income areas. And so you could say this is evidence that there's some kind of concentration occurring, where people's migration patterns are such that people are moving into high income areas and the incomes there are increasing. Well, in our third place, this is now in the south side, we see that populations are shrinking, incomes, and this is income relative to the citywide average. Incomes are lagging a bit, but the selection is pretty consistently negative, which is then telling us that the people who are leaving, they are leaving high income parts of this area. And meanwhile, incomes are dropping. So this would be some evidence of flight. And then for our last region, now this is a neighborhood in Chicago where there is, colloquially, people have talked about these neighborhoods as historically having a lot of gentrification. We can start to actually see that a bit in the data, where the population growth has been pretty low, pretty modest. Income growth, depending on where you are, has been quite substantial. And as we saw from that last map, we do have some selection effects, right? So this is this area here. So where we have low, we have high, and where we have high, we have low. This is resulting in almost zero, pretty negligible selection. But from that micro data, we know that there's quite a bit of sorting occurring here, and potentially even displacement. So this is all to say that this introduces like a complementary data set that can be helpful in generating hypotheses of local urban change that when you view next to the rest of the data starts to paint a pretty clear picture. And you can get there without having any qualitative knowledge of this. Okay. So now just to take a step back and look at things a bit more quantitatively. So this plot here on the left is just the distribution of selection effects across the city, across the MSA. And so it's quite crazy that for such what we would think of as a complex process, it's almost a Gaussian, not quite. There's a bit of skew, the tails are a bit heavy, but we have selection that is centered around zero. So maybe this hypothesis that Chicago is stagnating isn't true, but at the very least, we see some competing effects. We see that these tails become slightly slimmer as we aggregate, which is what we would expect from like the central limit theorem. But what these heavy tails are telling us is that these selection effects are really persistent causing this accumulation across years. And so from this data, there's a couple of questions that we can ask. One is really just like, how large are these selection effects relative to the overall growth? And so we're going to calculate that using this value rho. This is really just that selection magnitude. So we compute the selection, we take the absolute value, and then we divide by the growth rate of the city. So now we're reporting it as a percentage, essentially. And so we see, on average, this is about 15%. So 15% of the growth of this tract can be explained by selection across the block groups. But there's quite a bit of variation. When we ask the same questions for higher levels of aggregation, that quantity starts to decrease, but doesn't quite go to zero. And so this is what we can tell from this is, yes, selection effects are stronger at smaller scales. And there's quite a bit, you notice more sorting at the smaller sizes. Yeah. And then we can ask a different question, which then is how are these selection effects then resulting in observable selection on the city scale? And so this is really a question of like, well, why is this centered at zero if things are so heterogeneous? And so we see here, if we set up that price equation and ask what each of the terms are, that's what each of these values are here. We see that the selection effects in the aggregate are quite small. All that variation is being hidden by this averaging. So another way to think about this is how consistently are people making these selection choices, and then how consistent are these selection effects across space. And so we see, yeah, they're pretty close to zero. This is slightly negative, so people have a slight preference for low-income block groups. This is slightly positive, so people have a slight preference for high-income community areas within counties. But then this starts to get at some questions that we talked about a little bit earlier. Some questions of like, what is the proper scale? If we're asking, how are people's perceptions of the city influencing their residential choices? This measure can start to help us uncover that. Because you can imagine, for example, in Chicago is a city where, the dominant narrative of urban change is between these community areas. And so for those familiar with the city, you have the West Loop, you have places like Logan Square, Lincoln Park, where there's been historically, or at least in the last 15 years, a lot of investment. Then you have some other neighborhoods, maybe in the South or West side. But my point is that we conceptualize of the city as being relationally between community areas. Whereas if we ask a similar question for a place like New York City, it might be between the counties, between the boroughs. Whereas a place like Los Angeles, well, the notion of a neighborhood starts to break down a little bit there. People think about the city more on like a block by block, a neighborhood by neighborhood scale. So the question then is, does that perception of the city, does that show up in this data? Of course, these selection effects don't exist in a vacuum. They are a response to histories, to the prevailing demographics of the neighborhood. And so really trying to understand, how do policy choices, how do investment choices, how do existing POIs then help predict these selection choices, and then how do these selection choices then influence future investment and policy decisions? And then of course we can just swap out the terms we use in these aggregations, maybe do a similar disaggregation for some kind of identity or education levels or so on. And so I promised you guys a bit of result on the income selection. And so I skipped over this, but those selection effects theoretically have a close relationship to changes in inequality. And when we regress those income selection effects on changes in Gini, we see a nice agreement. That's to say that that these compositional effects that we're seeing in this population selection, whatever the resulting changes in income allocation, is resulting also in changes in spatial inequality. And just, you know, when we say that, for example, a place with negative covariance is becoming more spatially equal, we're not saying that like it's truly becoming a more equal place. It could just be because there's like a lot of replacement sorting and so on. So I don't think this is necessarily like a happy result if we're interested in studying inequality. Okay, so that's it. Just to conclude, this talk was broken into two parts. The first was this providing these snapshots of urban complexity using this information-theoretic measure. And then the second part of this talk is then measuring how does that complexity change over time through selection effects. So that if you were developing a model or a theory of residential selection, these measures here could help you get an idea in the data of how complex that those models would have to be to like properly describe the features we see, both instantaneously and temporal and over time. And so these are the collaborators. These three did like 97% of that first part of the talk. And then Laura and I worked mostly on the second part together. So, and these are, he's based at Arizona State University. So yeah, that's it. This paper is online. So this is a QR code for the preprint. And then the preprint for the latter half of the talk should be coming out in a couple of days. So yeah.
Questions? No. Also, if people online have questions, you can either unmute or post to the chat.
Yep.
So question about the Gale divergence stuff at slide 13. So I'll just wait for it to come. Yes, so in this figure, what is the four different bins, like the colors? It's a distance between what two parameters? Is it just the three neighborhoods that you've chosen?
Talking about this one or this one?
The one on the right, yeah.
Okay. You're asking the bins up here or like
Yeah, the bins, yeah. So the bins, so the colors that you've chosen are based on distances between what two distributions?
So you have the distribution, this distribution, which you could express it rather in terms of log incomes, in terms of the original bins. Right. So there's like a matching there that you do. It would probably still look something, it'd look Gaussian, but with, you know, the measure is not now linear, so you'll have some weird distortion. But then you're just computing the distance between that and each of these for every spatial unit. So this is just three examples, but you could get these distributions for every single spatial unit. And actually, this is how the ACS reports the data.
Mm-hmm. Yeah. So it's essentially just a citywide distribution, and you're comparing that to the, I guess the blocks that you have created in that map, so the distributions in those specific blocks.
Yeah, I guess like we haven't we've plotted them, but these are the block groups that like are defined by the ACS. Yeah.
Okay.
Yeah.
So we have a question from online from Esteban. He says, "Thank you for your talk. In your opinion, how much of the change you see in 2020 in the first part of the talk could be due to differential privacy method the Bureau started in 2020?
Oh. Could you describe what that method introduced? Because I haven't heard of this.
Hi, can you hear me? So in 2020, the Census Bureau started applying noise to the data within CBGs to increment the differential privacy, let's say, method to, let's say, obscure a little bit the distributions of income, the income within CBGs. So that was a radical change. And a lot of people are complaining that the data right now has more noise, which might be related to the fact that you found that there's much more information right now.
Yeah, so would that be noise? Is that only in the upper bins of the distribution, or do they apply that like uniformly across the whole?
It's uniformly.
Okay, I would have to ask my collaborators because they did most of the analysis, but the nice thing about these, well, let me think about it for a sec. Because that definitely would scramble the distribution. Yeah, I think it's something that we could test by then probably aggregating to the tract level and then seeing how well the complexity scales. Because then that aggregating should then start to, you know, average out that noise. So there's ways that we can test the magnitude of this effect, but I'm not sure off the top of my head whether, like, how much, like, what is the threshold of noise that you could introduce that would cause, let's go back to it, that would cause, you know, some cities to, yeah, I mean, for example, like these outliers have increased by almost like a nits of information, which is quite a bit. So I would think you'd have to add quite a bit of noise to get that big of a bit difference. So I'm sure it had a bit of an effect, but probably not large enough to generate this big of a difference in the data, but we can go back and test that.
Yeah.
There's another question here, right? Yeah. I appreciated how thoroughly you investigated heterogeneity across scales and its consequences for how we understand the complexity of cities. Sort of related, I'm curious what you think the consequences of the increase in complexity you mentioned is on policy, governance, and life in the city. This is a really great question. We talked about this a little bit in the paper. What you're getting at is like just a question of polarization. So how important is it that our cities are becoming more polar, that our cities are becoming, that places within our city are becoming more different from each other? I think that's what you're asking. Yeah, I think that's like the whole point of studying this is to better effectuate policy. You really need to understand like how severe and how quickly that problem is growing. Just in order to avoid like creating enclaves in cities where where social trust is eroding, and that's usually what happens when you have people that become increasingly isolated. So this is to more thoroughly consider that, you'd of course have to do mobility studies, right? And there's some people in the room who think about this. You know, as places become more polarized, are people's mobility patterns more polar? So there's a bit of a larger puzzle there that needs to be solved. But yeah, I generally think this is why we do it. Was there another question up here?
Can you go one slide after this one?
Yeah.
The next one, sorry. No, so before, I think, yeah, this one, yeah. So let me try to, because this one goes a bit confusing to me in the sense of, so what you are saying here is that this difference between the probabilities is like, so what for me strikes me is that Los Angeles, Chicago, and New York are the same for the three, so they have the same behavior. Because why do you think is that? Because I thought that like this would be something also related to how specifically in the city these regions are distributed. And I know that, for example, like Los Angeles, that you don't have a center, or in New York that is different distributions of, I don't know. I think that like it just strikes me that the three of them are quite similar. Like, do you think that there is a reason of that this is kind of universal or not? Are there cities that this is not the case? I don't know.
Yeah, so and I think this question also is related to Esteban's point too, is how much noise in the data would we expect to couple into these measures of complexity? And I think the one that would really matter for us is not necessarily how people are spatially, you know, whether that by density, how they spatially allocated. It's really a matter of like how concentrated are certain income groups. So you know, thinking back to this really high income bin, they were extremely concentrated in like 3 parts of New York City. I know this to be true, like in Chicago, we also have, or in the Chicago MSA, we have very few places that are known to be where people are concentrated. So this is to say that I think yeah, this is saying there's quite a bit of regularity in how our cities are spatially, how people are spatially sorted within cities. And it's pretty consistent across even urban morphologies like your New York or your Boston or your LA and Phoenix.
Yeah.
So yeah.
And this is more a very simple question, just because I'm still trying to wrap my head around the idea of the selection in the last part. So if you can come back to one of the last slides when you were comparing the 4 cases, and you had the selection was almost close to 0. This one, not here.
Oh, sorry.
Yeah, okay. This one, sorry, the next one. Yeah, this one.
Yeah.
So the last one.
This one.
Yeah. So the selection being close to 0.
Yeah.
Does that mean that people, like, can you explain to me again what that means?
Yeah.
Because I think I'm just trying to wrap my head a little bit. What does this, I don't know.
So let's start actually with this guy because
Okay.
it's really positive. So this means that both at track level, across block groups and across tracks, people are moving more into high income areas. Now that could be from one of 2 things that I didn't really talk about here. That could be either like high income areas are attracting a few people, or many people are moving into slightly high income areas. So like the question of magnitude, there's 2 sources of magnitude here. But we can say like consistently people are moving, you know. Right. Now that's because we see here this plus orange is super orange.
Yeah.
Right. But here we have now something that's slightly purple, slightly orange. So people are picking low income. Sorry, let's start here. People are picking high income tracks within a community, but within those tracks, they're really just picking wherever the cheapest.
Okay, I understand. Okay.
And so in terms of like how are people, if you want to use a physics term, diffusing across this place, what's influencing that diffusion is different. And you could say that it's happening more. It's happening more here because there's less of an attraction to income, even if it's slightly positive. Yeah.
Okay, now I can understand. Thank you.
Yeah, I'll just leave that up there.
Thank you.
Any other questions? Yeah.
Also about the case study. And I was kind of wondering, since you were doing the case study on Chicago, if you try to validate your results by, I mean, I know you already put like gentrification, but I kind of put my question before I saw that you have a gentrification specific. But so like, are you looking at anything specific where, I don't know, for some reason, let's say like school districts that are really good, people are moving in there, and you're seeing that the people who are moving into school districts are maybe like the somewhat lower income, but maybe it's still an affordable area. So yeah, I think I was just thinking if you did like any connection with like further but lower level.
Yeah. So in short, no, but this work was really to like demonstrate the calculation, how it works and so on. But no, this is exactly the next step, is to think like what forms of like physical and human capital are like really driving these changes. And of course, another step is to create like a basic null model. Maybe we have just like a basic diffusion. We have some kind of POI attraction type model, throw in some infrastructure barriers and see, whether like what is the minimal amount of amenities maybe, or homophilous preferences to throw in to like generate this magnitude of effect. So yeah, those are really like the next questions. And then, but then there's also that question that you're raising of like, how does this fit in with other analyses of, and I haven't thought too much about that yet. So that's be nice to talk about that a bit more afterwards. Yeah.
Any other last questions before we wrap up?
and do one. About this case study too. I was wondering in terms of the boundaries that, because these are kind of qualitative findings, right? In terms
Yeah.
of like the boundaries that you've mapped out, not the community, like the, because there was always that like special spatial resolution for Chicago, right?
Yeah, we're using those boundaries here.
Okay.
Yeah, these are
Okay.
the state. So the state of Illinois has community boundaries for the entire state, which gives us an extra layer. You could also replace that with zip codes, but zip codes are pretty inconsistent, but yeah.
Then never mind. I thought these were mapped out.
Well, there is kind of a point to make here of like, we could, so people in the gerrymandering research community, they do this really awesome, they have this really awesome method of like trying to essentially build arbitrary voting district maps, permuting these voter district maps, then asking how does that change our election outcomes. We can do something similar here where we can create like arbitrary intermediate scales. And this is getting at the modifiable area unit problem. Identifying like for this city, like what's the right scale? What are the right boundaries that keep these selection effects consistent? Maybe also probing like, what types of boundaries do you need to draw for selection effects to cancel out? You could play these games essentially, some of which have scientific merit.
Yeah, because I was thinking as you were describing this, like, because all like, as we talk about aggregating and disaggregating, even going to like the morphological level of like streets and like
Yeah.
trying to create boundaries that go beyond population statistics, but yeah. That'd be
Yeah.
hard, but interesting. Yeah.
Yeah, because there's a circularity there of like these boundaries determine how people move around the city. And then how they move around the city then determines these maps. And then these maps then inform future changes to that morphology. So there's a part of a puzzle here that we know. Yeah, so that's great points. Thank you.
Okay, thank you so much, Jordan, and thanks everyone for being here.